Hi, everyone. Thank you all for joining today's seminar. This will be our last for 2022. It is a pleasure to have Professor Wilfred van der Wiel with us today. Professor van der Wiel is a full professor of nanoelectronics and director of the Brain Center for Brain-Inspired Nano Systems at the University of Twente, the Netherlands. He holds a second professorship at the Institute of Physics at the University of Münster, Germany. His research focuses on unconventional electronics for efficient information processing. Professor van der Wiel is a pioneer in material learning at the nanoscale, realizing computational functionality and artificial intelligence in designless nanomaterial substrates through principles analogous to machine learning. So it's a great pleasure to have Professor van der Wiel here with us today. Before I hand it over to Wilfred, I would like to remind our audience that you can ask your questions either using the Q&A option of this webinar, or you can, at the end of the talk, just raise your hand. We will unmute you and you can directly ask your question. So with that, Wilfred, thank you very much for taking the time to join us, and I'm going to hand it over to you.
Thanks a lot, Farnaz, for this nice introduction and also for inviting me to this MIT.nano seminar series. It's really an honor and a pleasure to talk to you today. Unfortunately online, but on the other hand, it allows a lot of people to join. So good morning to Boston, and it's again, a pleasure to talk about this topic of material learning today. So maybe some of you may thought it's a kind of typo, that it should have been machine learning or so, but it's really material learning. And of course, there is an analogy with machine learning, and I hope to make that clear in the coming 45 minutes or so. Let me first go to the most important slide of today, and that is acknowledging my co-workers and also the funders. Where appropriate, I will point out people who have been playing an important role in the diverse activities. But as you can already see from the many people involved, it illustrates that this is really a multidisciplinary endeavor. My own background is in applied physics, physics engineering, but of course we touch upon things like computer science, electrical engineering, math, even chemical engineering, which makes this very nice and really enjoyable field of research, at least for myself. And you see also a lot of smiling faces here on the slide. Well, I'm not sure. It's probably not really very well known outside the Netherlands, but today is a very special day for the Dutch. Namely, it's the day of Saint Nicholas, or Sinterklaas, as we say, December 5th. It's not the same as Santa Claus, that you of course know very well, but probably the two are related. Saint Nicholas is the patron for children, so we normally celebrate that in the Netherlands. And the day of that celebrations, St. Nicholas Eve, is December 5th. So if you write that date down, the many different ways of writing down a date, but we could write it down December 5th as follows. But on the other hand, we can also make a little mathematical puzzle out of this. 2022 minus 12 minus 5. I guess not many of this distinguished audience will have a lot of trouble solving this mathematical puzzle. So I'm pretty sure you can solve this in a short time, but maybe if we write this date slightly different, and now as 2022 divided by 12 divided by 5, and without using your pocket calculator or iPhone, could you give it a try and solve this mathematical puzzle? And I understood the chat is open. Maybe Farnaz can have an eye on it. Are there any people who could solve this, well, a little bit more advanced, but still reasonable mathematical problem? Are there any results coming in?
Someone is saying around 850.
Around 850. Anyone more or less than 850? It's very courageous. Well, 33.7, maybe if you check it, if I made a mistake, but you can see this is, although maybe not the world's most difficult mathematical problem, it's definitely non-trivial for us humans to solve this right away. I would like you to forget about the 5th of December and focus on the screen very carefully. Don't look at me, look at the screen and focus what you just see. So I don't know whether it worked across the ocean, but I hope you saw something flashing. And again, I'll ask you, what did you see in this split second? Any rough description of what you saw? Please put it in the chat and let me know. Any idea what was just appearing on the screen for a very short amount of time?
So someone says, person with a big hat, Saint Nicholas, some red color in there, Christmas tree. These are some of.
Okay, answers coming in. Yeah, great. Well, these are pretty accurate descriptions. Thanks for joining this little experiment. Because indeed, there is a guy with a very big hat. Indeed, Saint Nicholas, very good. There is no Christmas tree yet. It could have been there. For the very good observers, maybe you can even recognize me behind this big beard and the glasses well hidden. It was actually taken exactly 10 years ago, this picture. And just an hour before preparing for this talk, I was wearing the same dress and addressing here the group members. So this talk is not gonna be about St. Nicholas all the time, but the point I would like to make is that a rather simple mathematical problem could already cause us quite serious problems. And on the other hand, a quite difficult task, recognizing an image for a tiny amount of time, is already pretty accurately solved by most of us. So that also shows, I think, very nicely the contrast between man-made information processing systems like, par excellence, digital computers, and our onboard computer, the human brain. And so our brain has evolved to really be very good at interpreting the environment, maybe not as precise, but making decisions based on very quick observations, like seeing Sinterklaas, for example, whereas our digital computers, on the other hand, are not exactly designed for that, but much better at solving exact calculations, doing logical operations and things like that. So also, what is very important to see if we look at further differences is that basically the structure of our computers is very different. Most notably, we have a separation of memory and processing, which is referred to as the famous von Neumann bottleneck. We'll see later that that is causing a lot of power consumption. Whereas in the brain, computing, information processing, maybe better, is much more distributed. So memory and processing are kind of blurred or co-located. The digital computer is a kind of implementation of the Turing machine, which is in essence a sequential machine. So every step is carried out one after the other. Whereas in the brain or the nervous system in general, a lot of things happen in parallel. That makes that although the individual elements, building blocks of the brain, the neurons, are not amazingly fast, maybe operating at 1 or 10 hertz, there's still a lot of things happening in parallel, and therefore the equivalent amount of operations per second is astronomically high. And in the case of digital computers, we have invested over decades a lot of energy and effort in making the individual components, and especially transistors, very fast. So they can operate maybe at gigahertz frequencies. But since it's a sequential machine, there are at the end limits to that. So what you see in the evolution of the computer is that also their parallelization has made an entrance, and you see now things like multi-core and parallelization also happening. But maybe the most intriguing fact of all is that this all happens in the brain at a very low power consumption. So typical power consumption of the brain is just about 20 watts. And if you would like to get a comparable amount of operations using CPUs, then the processing units, central processing units, you would easily get in kilowatts or even megawatt. So there is definitely something we can be inspired with from the brain. I want to make my first disclaimer of many. We are definitely not claiming that we even think coming close to the brain, or that we want to make a copy of the brain, that we understand the brain to begin with. But still, on an abstract level, there are definitely things that we can be inspired with and maybe try to apply in man-made systems. And this is really going to be not only very interesting from a scientific fundamental point of view, but also really from an application technological point of view. Because as you may know, a lot of today's machine learning is done by deep neural nets. You see a very simplistic picture of such a deep neural net here. So these systems consist of many artificial neurons. These are these nodes with many interconnects, and the whole process of machine learning in this example of feed-forward network is trying to find the right weights and biases in this mathematical model in order that some problem can be solved, like in this example, recognizing and classifying different animals. But in order to make these model work, you have to go to many examples, many training phases, learning a lot of weights, and do this iteratively. So many data need to be processed. And if you look at the evolution of AI, machine learning, and you follow this from the early days of these Alvin or Lynette, so convolutional neural networks for image recognition, handwritten data, and now look at more recent examples like AlphaGo, AlphaGo 0. You see that there is really a drastic change in the trend of the amount of compute that is needed to train such machine learning systems, and in particular these deep neural nets. Whereas in the first decades, there was more or less a kind of same kind of increase as the famous Moore's law that refers to the hardware development. Now in the maybe last 10 years, you see that there is really the demand for compute is rising much faster than hardware can keep up with. So there's really a clear mismatch between demand for compute in these systems and the availability of hardware. So in principle, you could say, well, this is a kind of unsustainable direction. At soon, the availability of suitable hardware is going to be a real life bottleneck for the further development of these machine learning applications. Also here, maybe you know about this famous AlphaGo that I already mentioned before. Of course, amazing that this system of DeepMind can beat this poor guy in the game of Go. But if you look behind the screens, you see that this single person with a single brain of 20 watts has to fight this amount of computing power corresponding to 1 megawatt. So also there, we should not forget that all these successes come really with an impressive energy footprint. Here are some other examples to illustrate that. Maybe most telling is this example here on the right, that also in the Netherlands, they try to put data centers, so the Googles and the Facebooks of this world, of course, are very eager to put that in cold countries. But this example here shows that the foreseen data center close to in the year 2030 will consume more than twice the amount of electricity consumed by the city of Amsterdam. And there are many examples like that. Well, then you could still argue if you are in a centralized data center, then you can still maybe generate some green energy. But imagine that you are in an electric vehicle and you want to make it autonomous. You see here in this example that there is a lot of hardware and also a lot of energy needed to realize it. So when we say if you really want to apply this technology, AI at the edge, decentralized, like for example in these autonomous vehicles, it's really important that you work on the hardware as well, that you work on a small energy consumption, also a small footprint, so that not a lot of volume and battery capacity is taken simply by compute. So, point that I want to make, think about hardware. The future of AI is hardware, or the future of hardware is AI, as put out here by this person from IBM. And well, this is a message that I think is very well understood by the academic world, but also by industry. So here you see a couple of examples that already go back quite a few years of AI accelerators. So hardware that is really designed to try to speed up, but also lower the power consumption of typical machine learning related tasks, in particular for the specialist matrix vector multiplications, multiply and accumulate operations that you find back a lot in these deep neural network calculation, training, and inference. So what they do is basically optimize architectures to try to circumvent this von Neumann bottleneck, which is the separation between processing and memory. So what they do is try to basically, in principle, parallelize operations. So you will see that often is a multi-core kind of design. Importantly, most of these solutions are still digital, so they work with zeros and ones, with bits. They're based on the conventional building blocks of digital computers, which are transistors and also passive components. Most of them are silicon-based, so silicon is really the base material for modern CMOS, for modern semiconductor industry. And of course, although very impressive results have been reported, we are still quite far away from the brain's efficiency. So the point I want to make, and now is when I get to material learning, is whether we can gain something by basically forget about the conventional building blocks and try to use materials as the ultimate computing information processing substrate, or as sometimes it's called, the material is the machine. So we are familiar with learning in the biological sense. Most of us also have heard about this machine learning and this neural nets. But what about material learning? Can we directly start to tune and to change materials so that they can carry out information processing tasks? So in particular, can we exploit the physical properties, maybe even chemical, electrochemical properties of materials to compute beyond simply using them as on, off, 1, 0 kind of switches? Another intriguing fundamental question is there really something unique about this organic material that the brain is made of? Or is it just a choice of nature? And can we as engineers maybe emulate that and maybe even improve on that? And yeah, that connects to that question. So if we have something that we could call intelligent, and what that means I'll come to in a moment, would that mean that we can really compute efficiently and even more efficiently than we do today? And could that perhaps contribute to that kind of computing catastrophe that I've just been referring to? Well, intelligent matter sounds very heavy, sounds very intriguing. Maybe I should start with maybe another kind of disclaimer and give you a more or less engineer's definition of what we could call intelligent in the framework of matter. And this is worked out in a perspective paper that was written by my colleagues in Münster and myself, in which we kind of outlined the rough idea of what maybe are the necessary elements of materials in order to call them intelligent. So there we argue that we need some mechanism for sensing. We need some mechanism for actuation. So in order to respond to a certain stimulus, we may also want to have some kind of feedback enabled by a network property. In order to take decisions, it's very important that these materials also have some nonlinearity and a certain degree of complexity. And if you really want to have a system that can autonomously learn and adjust to the environment over a longer period of time, you would also like to have a long-term memory. And so what we argue there is these are necessary ingredients if you want to talk in an engineering sense, again, about intelligent matter, excuse me. So what could we distinguish then if we try to categorize matter? So if you have the lowest class of complexity, so to say, those would be materials where the functionality is only derived from their structure, from their shape and structure. So think about a wooden club or some flint tool or something like that. The next stage in complexity would be responsive matter that would be able to react to a certain external stimulus. So in this cartoon, you see a kind of light coming in, and as an actuation, as a response, you see some light coming out. Maybe the wavelength is different. There is a response. The response is always the same. It's kind of one-trick pony, but it's already, it has some functionality and it interacts with the environment. Now, if you have a material that's able to adapt, that is able to maybe have multi-sensory input, so it can start to adapt depending on combination or timing of the stimuli, we could talk about an adaptive material. So it will be able to learn, but the evolution of the properties is still directly related to the external stimuli. Then finally, we come to the highest level of complexity in this framework, where we could talk about intelligent matter. And that's also where there is this long-term memory. And then you could imagine that even without direct external stimuli, the system, the material could learn and start to adapt over a longer amount of times, even autonomously, to a changing environment, and really adapts its responses to its history. This is the framework in which we like to work, and I come now to our efforts that started about 7-8 years ago in our lab, where we didn't have this kind of very clear intelligent matter picture yet, but we were interested to get functionality out of a disordered system and try, instead of completely designing a nanostructure a priori, see whether we could make a disordered system and then a posteriori could get functionality out of it by doing in situ tuning of its parameters. You will see that in these devices that I'm going to discuss, there is no local memory yet. So when I talk about tuning the device, when I talk about configurations, I'm really talking about electrostatic changes of these nanoelectronic devices. So we are not there yet to incorporate local memory, which is definitely on our wish list, but just for you to put it in the right perspective. So what you see here in the cartoon on the right is a system, a network, a pile of gold nanoparticles with some organic shell around it, which is deposited on a couple of gold electrodes. So you can't see it here, but there is an opening in the middle. So basically this disordered network bridges these electrodes. So the reason why we tried and we started with this system was that we know the behavior of these single nanoparticles very well if we apply a source drain voltage across them. We know that they act as nonlinear switches, be it at very low temperature. And the reason is Coulomb blockade. So if you take a single gold nanoparticle, you will see that because it's so small, the energy to add an individual electron to the island is finite. You need an amount, the charging energy, which is given by E squared over C, where E is the electron charge and C is the total capacitance of the island. You need that amount of energy to add an individual electron. And the island is so small that you will start noticing the repulsion between electrons that are already on the island and the one that you like to add. This is therefore a completely classical effect as opposed to quantum. So it's not a quantum confinement effect, but purely on classical grounds, you would expect this discrete levels in your electrostatic potential. Now it's interesting, if you align the source and drain contacts of such a single island in this way, you see that electrons can tunnel one by one through the island. But if you slightly shift the potential levels, then you will see that the system can be in blockade. So if you plot now the current through such an island, through such a gold nanoparticle as function of the potential, you shift the potential level, you see very spiky behavior when it's on and a blockaded region, Coulomb blockaded region, when it's off. So this is the physics behind it. What you need to remember is basically we have now a periodic, very nonlinear switch that we understand on a single particle level, but we basically have no clue whatsoever how it behaves if you make this network out of it. And that's the whole idea. We would like to see whether this complexity, whether the nonlinearity, the tunability gives us enough maneuvering space to get functionality out of it. And as it says here, as proof of principle, we wanted to see Boolean logic. So if we don't have a mathematical model, physical description of this network, we need another way of finding out how we can tune this system. So maybe we can define some of these electrodes as inputs, some of them as outputs, and the other ones we can use to manipulate the electrostatic landscape of this network. You could do this completely brute force, randomly, trial and error, but what we tried to do was incorporate a so-called genetic algorithm or an artificial evolution, but apply that directly to the material substrate. So genetic algorithms are known from the machine learning, from the artificial intelligence community, but there they are applied on models, on mathematical models. Here we basically insert the material substrate in the loop. So what we do is we apply a physical input, like a voltage. We also try a couple of physical configurations, which in our case are voltages also applied to this network, and we measure a physical output, which in our case is a current. Then this is brought to a conventional digital computer, and we map the physical output to digital data and compare the actual physical output with the desired output. So we have a comparison, we have a kind of fitness that we can assign, or an error function. And based on that, we start to make changes to the configuration, what we call the genotype, and play all kinds of tricks that we know from genetics, sexual reproduction. So we have a couple of these configurations, we compare them, we select the best. Maybe some of them we start to combine, like a kind of crossbreeding. Also, we insert sudden changes, like mutations, in order to don't get stuck in a local optimum. So in that iteration step, that generation, we try all kinds of different things, and as the result of that, we apply again to the material, and then the whole circus start again. There's in general also a possible step here. We normally don't change the input. We normally have a fixed input and only change the configuration. And now the idea is, the hope is, the expectation is, if the system is complex enough, has tunability enough, is that after a couple of generations, iterations, this material is able to approach the desired output. Again, in our case, we try to look for Boolean logic. So we hold this whole procedure when we have reached a fitness that is satisfactory for our purpose. So here again, here's the device schematic. We have two inputs in this case for applying the voltage inputs, which are given here on the right. We want to encode different Boolean logic gates that you see here in the bottom. We encode one with a high voltage input and a low with a 0 voltage input. And you see here, we scan through the total input space as a function of time. And if, for example, we want to realize an AND gate, we only want to have a high output if both of the inputs are high. So like in this example, this is the solid line represents the desired output. And what you see here is schematically the configuration that we apply to these 6 voltages here in the periphery and to the back gate. And the output here is current. Here we're not really there yet, but by adjusting a little bit more these configurations, what we like to have is that we really match the desired output signal. And here are the results of this network, but this has been done on a number of similar devices. And you can see, be it at very low temperature for enabling this Coulomb blockade, and we can realize inverters like you see here on the top, or these 6 Boolean logic gates. Also the notoriously hard XOR, XNOR, which are nonlinear gates, can be realized. And as a matter of fact, in principle, you can, and we also have shown all 16 possible truth tables that you can in principle make with a 2 input, 1 output binary system. So this shows that, a posteriori, we can indeed insert this functionality. Of course, it's an academic proof of principle. It's very impractical to work with nanoparticles, to work at very low temperature. But just to show that, by playing with the parameters, with the voltages in situ, we can exploit the complexity and nonlinearity of this black box system. In principle, we don't have a user's manual of how it exactly works, but very much in the same spirit as machine learning, we work towards a functionality by learning, in this case, material learning procedure. Again, I stress that the weights, the kind of weights, which in this case are the configurations, are stored externally. So there is no local memory. So this is not helpful for solving the von Neumann bottleneck. Of course, we very much would like to have that, maybe a network that we can really change plastically so that we don't need to store the weights and capture them all the time. Definitely on our wish list, we are not there yet. Okay, so we have shown some proof of principle, and as I said, it's not ideal system if you really think about serious applications. So maybe a step closer to that is the next system that I would like to introduce, which you see on the right, which is a silicon-based system. We don't have now a network of nanoparticles, but instead we have a network of implanted dopants inside the silicon that we address again electrically by these electrodes in the periphery. So the electrode structure is very similar to the one on the left. The overall device size is also very similar. This is about 200, 250 nanometer. But the nonlinearity is now derived from transport through this disordered dopant network. Here you see again the device. This is a scanning electron micrograph, and here a schematic cross-section of the device. So we implant, in this case, boron, conventional ion implantation, and we get naturally a gradient of the concentration. When we make the electrodes on top, we contact them at the surface where the concentration is relatively high so that we can get an ohmic contact here. But we would like to explore the central region in a doping regime that is relatively low, so that not the typical band conduction dominates, but rather the nonlinear hopping transport is the dominant transport mechanism. This you can see here on the right. So this is measured here just between two electrodes, but you see that it's the IV characteristics, so the current drain, the current voltage characteristics are very nonlinear, and also nonlinear up to relatively high temperature, at least if you compare with our previous results for the gold nanoparticles. So that's a nice thing because we can operate now, for example, at liquid nitrogen temperature, 77 K, which is much easier experimentally, also cheaper. And we work in silicon, which is of course also a bonus because, as I said in the beginning, basically all standard electronics is silicon-based. Here's some kind of underlying evidence that we are really dealing with 2D variable range mod hopping in this regime. I'll go over that a bit quickly here, but just to show that we are not in the typical band conduction regime that is normally used in conventional electronics. So in order to visualize a little bit how we think what is going on in these structures is here the inputs. You encode your problem like recognizing a digit as the inputs of your device. You read out the output as current, and then by changing the configuration voltages, you basically shape this landscape, this kind of hilly landscape in such a way that the desired output is obtained. And this could be then an encoded answer to your problem. We make, again, use of the nonlinearity. We also have things like negative differential resistance, so all these typical things that normally only pop up in nonlinear, in more complex systems, and enjoy the nanoscale and also the silicon environment of the system. Again, what we manipulate, we think, is only the electrostatic landscape, not the actual position or coupling of the dopants for now. So we repeated our standard benchmark task, the Boolean logic, in the same fashion as before. And as you can see here, we do indeed obtain these Boolean logic gates. And by pushing our device to the limit, we can also squeeze out behavior at room temperature. More recently, nowadays in our lab, we can indeed do these experiments at room temperature. So we came again a little bit farther than liquid nitrogen, which is of course really a must if you want to apply this like at the edge and in real life applications. So that's very useful. Of course, yeah, Boolean logic, we know how to make it with standard electronics. So it's really a benchmark task, but not really a very interesting result in itself. But the exclusive OR is still noteworthy because you can also interpret the XOR as a nonlinear classification problem. So another way of kind of visualize the truth table of the XOR is as follows. So you see, if this is high and blue is low, this is basically showing the XOR. But you can also interpret this as a classification problem. So how to separate these red balls from the blue squares. And you will see that even if you try a very long time, there is no linear decision boundary. So you have to have something like this to separate these two classes. So we call this a linearly inseparable classification problem. What you could do is now do a transformation to a higher dimensional space to make this problem suddenly linearly classifiable. So as you can see here, you have now a linear plane that separates the two classes. Of course, the question is how to find this transformation. But once you have it, then it basically becomes a very trivial exercise to separate and classify these two classes. So making an excursion from 2D to 3D and back to 1D is a kind of trick that you can apply to make a non-linear classification problem more simple and at the end linearly separable. This is a kind of general approach. If you blow up the dimensional space, sometimes it becomes really easier to solve a certain problem. And so that's what we do now in our device. At least this is a way of looking at it. Instead of finding an explicit analytical transformation, we let the work be done by the material, by this high-dimensional potential landscape. We put the XOR problem as input, and we let basically the material do the calculation for us and the classification. And so that's a kind of the philosophy. Although we don't have this local memory yet, so we don't work, and we haven't shown really a solution to the von Neumann bottleneck. But what we like to stress is that by exploiting this nonlinearity, this complexity, we can basically cut on the number of explicit calculation steps. We can do kind of one-shot computations that hopefully help to make information processing more efficient, less steps. And of course, if we combine that with local memory, it would even be better. So what we showed was applying this system now to a little bit more advanced problem. This is the MNIST handwritten digit database that is used a lot, although already quite some time ago now, for benchmarking machine learning algorithms, in particular convolutional neural nets. So what we did was using our network now as a kind of feature extractor. So very much similar to what we see in convolutional neural networks, but also in biological neural nets, like here in the visual center of a mammalian brain. where certain neurons or columns of neurons react very specifically to a rather abstract feature, like the orientation of this bar. So what we did was here designing and configuring, configuring is a better word than designing, configuring the network such that it reacts to a very specific input pattern now encoded by 4 electrodes at the input. And we had to design 16 different feature extractors, each of them responding most clearly to one of these 16 input patterns. Then, because we are limited in the amount of inputs, we scan these digits, we multiply every window by these 16 feature extractors, so we blow up the feature and the feature space tremendously. But having done so, after that, a linear classification step becomes much easier. So if we look at the results, as illustrated here with test data, we see that we can improve quite a bit. Excuse me for a moment. Excuse me. We can improve quite a bit in comparison to pure linear classification. And so if you only do a linear classification, finding these digits, you find like an 88% accuracy. Now inserting this step, this kind of blowing up the dimensional space with our materials network, we can improve on that. Just to put it in perspective, of course, if you go to purely deep neural network approach, you can do much better. We argue that if everything is optimized, we could realistically get a projected data operation speeds of 100 tera operations per second per watt, which is already approaching this efficiency of the brain. Of course, there is a lot of buts and disclaimers here, but in principle, this is an interesting way to go, because you condense a lot of operations in the complexity and nonlinearity of this device. Okay, I've been using this evolutionary approach to train these devices. There are different ways of doing that. This is an example that you can make a surrogate model of our physical device by learning a conventional deep neural network. So basically you make a clone or a surrogate model of the device. Once you have a device that really walks and talks like the physical device, you can now do a second learning phase where you now use the configuration voltages as the learnable parameters, and then find the set of configuration voltages that you would need for a certain functionality. So in this way, we have, for example, solved this classification problem where we would like to separate these two classes, the black and the white data. Now the inputs are not just binary, but more continuous. And you also see this is a nonlinear classification problem because the decision boundary is clearly nonlinear. The device solves for you the classification by a simple output current level. So high output, which you also see here in the heat map, high current corresponds with the inner class and low current corresponds with the data along the perimeter. So again, you do a kind of one-shot calculation here for solving a nonlinear classification step. Another problem that we could solve in this way using the surrogate model is encoding in one device and one setting, basically a feature extractor that is able to recognize 16 different patterns, input patterns, the same that we used for MNIST, but now for one and the same setting of the device. So the output analog produces analog output currents that correspond now with all these 16 different patterns. And so depending on the current level, you can immediately see what feature you are applying to the system. Last, I'll show you a system where we hope that we can really get rid of this external computer and that is doing gradient descent directly in matter. So we find the gradient by doing a slight perturbation of the input parameters. We use a homodyne detection or lock-in detection to determine the gradient, so all the derivatives, partial derivatives relative to these inputs. We can do this in principle in parallel. When we then multiply this gradient with the derivative of the error function relative to the output current and some learning parameter, we can basically generate an update rule for the DC inputs. And then if we imply this all in hardware, we can in principle realize an update and online learning system for the material. So this would be really then a next step forward so that we can get rid of external digital computing. I'm running very late, so apologies for that. Let me just show that we also can realize Boolean logic again with this. And I think I should stop here, wrap up and say, well, I hope I've given you some idea what I mean by material learning, that we really try to exploit intrinsic nonlinear physical properties to process information, that we use in principle designless systems for that makes them defect tolerant to some level. That also means that we have to train and learn every individual device, which is in some cases, of course, also a downside. What we really are after is small footprint, higher energy efficiency, low latency, and hopefully contribute to these outstanding issues. With that, thank you very much for your attention.
Thank you, Wilfred, for a very, very interesting talk. So we're going to have a few minutes for questions. You can again type your question through the Q&A option or raise your hand directly and we will unmute you to ask your questions. So there are already a couple of questions posted, so I'm going to go through some of those. So one of the questions is asking if you can make any connection between quantum computing and materials learning.
Right. Okay. So you could basically see, at least that's the way I see it, as quantum computing as a very specific way of exploiting physical properties of matter, right? And in the case of quantum computing, specifically, it's quantum coherence, it's quantum superposition, it's entanglement that you really try to exploit for finally speeding up, even exponentially, certain algorithms. So it's a kind of subset, of course, a very well-developed and a standalone field by itself of exploiting the physical properties. If you look at the general quantum computing scheme, it's still a sequential computer, but the parallelism there is coming really from this quantum superpositions. So yeah, there are definitely connections.
Thank you. So another question is asking, would fuzzy logic gates and logic facilitate intelligent matter design, along with potential ability for learning or adaptation to changing inputs?
Yeah, I think that's a great idea. I'm, to be honest, not a very I'm not a specialist with fuzzy logic, or but I think the fact that we indeed do not, for many applications, we do not have to be super precise, and we don't need to have weights all the time extremely accurately determined. So in that sense, for many applications, we can allow ourselves a certain degree of fuzziness. And I think that's why, especially, in the application field of doing these machine learning tasks, these material systems could come out very, very handy, because indeed, there is always some noise and there's always maybe some fluctuation, but to some degree, we can still, maybe on a statistical level, still come out with meaningful results. So I hope that is somewhat of an answer to that question.
Thank you. Another question, have you considered analog computing using your devices?
So if analog, okay, so in a way, this is analog. Yeah? So if you would call this computing, then you could say, okay, this is kind of analog computing because we don't use the digital framework. If analog, if it's meant analog in memory computing, I don't know, maybe like people use with memristors, and if the question is referring to that, I could say that we are looking at combining our systems with this analog electronics, and then specifically analog in memory computing, and even more specific, memristor crossbar arrays, because these are very good at carrying out linear operations, these matrix vector multiplication or multiply and accumulate operations. Whereas we think maybe the biggest added value in our devices is more in this nonlinearity and this more reservoir property, tunable reservoir property that is related to this hyperdimensional space. So combining this with analog computing is very concretely on our radar. For example, collaborations in European projects with, for example, IBM electronically, but also in the photonics domain. So combining this with analog photonic circuitry.
Great. So the next question is asking if you can provide some perspectives on other material systems and property modifications that you envision using in addition to gold nanoparticles and silicon dopant system and silicon.
That's a great question. So you probably heard me say quite a number of times that we would like to work at room temperature, which basically now works for the silicon device, but that we also want to have local memory. And I think this is still one of the main lacking ingredients in our systems, that we do not have a local materials mechanism for storing basically the weights or this potential landscape. So for me, there's a big focus on materials where we could incorporate that local memory functionality. So then you could think of adding more like, in the electric domain, this would be then a kind of floating gate or flash-like functionality. You could think of maybe ferroelectric materials or phase change materials or resistive raw materials. Maybe even a completely different go to the organic or electrochemical domain, where you can combine both charge and ion transport, where the ion transport is very often at much longer time scales than the electron transport. So to be honest, I don't have a very very specific material system, but it should have added value in one of these domains that I summarized to get long-term memory, or even short-term memory. What people sometimes call fading memory is also very interesting. If you want to process time-dependent signals, you also are interested in time dynamics. So if you can build in these networks also this time dynamics at time scales that are interesting for the input signals that you like to process, this is also definitely on the wish list.
Wonderful. So maybe we'll end with two more questions. So for the dopant version that you showed, is the nanoscale required for the devices? And if so, are there nanofabrication challenges ahead, for example, in terms of scaling?
Right. Whoops. Let me see where I got. 1 second. These are some backup slides. Let me see. Yes, also very good question. The nanoscale is quite important because what you see is there is if you make the device larger, at least that's what we see in simulations, at some moment, basically this kind of critical percolative paths are being washed out. So the whole system behaves more like a kind of homogeneous soup, so to say, which is also which is harder to manipulate from the periphery. Because the farther away these electrodes get, also the harder it is, the voltage drop per hopping typical next neighbor or next neighbor hops becomes less. So the tunability goes down and you get more a kind of smeared out behavior. That has maybe more to do with our limitations in lithography. And that was, I think, the second half of the question, which indeed is a point. So if you could think more of a kind of 3D system where you are also able to maybe probe in the middle or even in a kind of 3D kind of lattice way, maybe then it is not so critical. Of course, many people say if you really want to compete with the brain, then you have to go 3D. I agree. For now, that is for us still a couple of bridges too far. But indeed, the dimensions, they give us some limitations, and yeah.
Thank you. And one last question. How do you determine the specifications needed in your material design that will have the properties you're looking for?
Right. That's also a very good one. So the short answer is a priori, we don't know. It's a little bit similar to designing the meta parameters of a neural network model. Right, so there it's also kind of maybe art that how many layers do you want, how many nodes do you want in a layer, how sparsely interconnected you want. I mean, there's maybe some gut feelings, but it's also not a pure science, right? So in our case, we try to of course, we are limited by the amount of inputs and outputs, so that determines what kind of problems we even dare to address. And then maybe the most systematic thing that we have done so far is seeing what the class of classification problems we can solve with a single device. So we can use quite precise or accurate mathematical benchmark tasks like VC dimension, which basically says, okay, how many binary classifications can you do? And then you see that a single device can do up to 5 or 6 points in a two-dimensional space and classify them. Interestingly enough, then if you start to interconnect multiple devices, so multiple networks, and admittedly we do that so far only in simulation, so using these circuit models, but we see that then we can address and solve more complicated tasks. So we do see some increased IQ, if you like to call it like that, if you start to combine. So that gives us hope that yeah, if we need high complexity, then interconnecting these things may be a way to go. But yeah, for now, it's that's a little bit more at the trial and error level, I have to admit.
Great, thank you. So this is all the time we have for the questions. Thank you again, Wilfred, for a wonderful, wonderful talk. And thank you to our audience for joining today.
My pleasure. Thanks a lot.
Thank you.
Bye.